March 31st, 1945. Frankfurt Rhein Main Airfield, Germany. Messerschmitt test pilot Hans Fay brought the sleek, unpainted jet fighter to a stop on the American-controlled runway, his hands trembling slightly as he shut down the twin Junkers Jumo 004 engines. The 22 Messerschmitt Me-262 fighters, scheduled to fly east to Neuburg that morning, would depart without him. 4 pilots had already taken off before Fay made his decision, but instead of following his comrades southeast toward temporary safety, he had turned northwest, toward the Americans, toward defection. The aircraft that rolled to a halt that spring afternoon represented Germany's most advanced achievement in aviation technology, the world's first operational jet fighter, faster than any Allied aircraft by more than 120 miles per hour. Armed with 4 devastating 30mm cannons, a technological marvel that had given Luftwaffe pilots a fleeting, qualitative superiority in the dying months of the Third Reich. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within hours, American intelligence officers swarmed over the captured fighter, photographing every detail, measuring every component, cataloguing every system. This pristine example of German jet technology, bearing the Werk number 111711, would soon cross the Atlantic to Wright Field, Ohio, where American engineers would subject it to the most thorough examination ever conducted on enemy equipment. What they would discover in the months ahead would fundamentally alter their understanding not of German engineering excellence, but of German desperation. The Me-262 represented a Faustian bargain of breathtaking proportions. Germany's engineers had created an aircraft a generation ahead of its time, then crippled it with engines that barely lasted longer than a single day's flying time. The jet that Hans Fay delivered to the Americans would teach lessons the Germans already knew too well. Technical brilliance means nothing when strategic materials vanish. Advanced design cannot compensate for industrial collapse. And revolutionary weapons arrive too late to matter when introduced by a nation already defeated. The story of captured Me-262s in American hands reveals how wartime scarcity transforms engineering triumph into operational nightmare. It demonstrates the cruel mathematics of modern industrial warfare, where the nation with abundant resources will defeat the nation with superior technology every single time. And it exposes the final bitter irony of Germany's jet program. The engineers who created the world's first operational jet fighter understood perfectly that their masterpiece was fatally flawed. They simply had no choice but to build it anyway. The Messerschmitt Me-262 Schwalbe began its existence in 1938, before the Second World War transformed Europe into a charnel house. Messerschmitt Aktiengesellschafts design team, led by Dr. Waldemar Voigt, envisioned a revolutionary fighter aircraft powered by the jet engine, a technology that existed only in experimental form. Hans von Ohain had demonstrated the feasibility of jet propulsion in 1937 while working for the Heinkel Company. His He S-3B centrifugal jet engine proved that turbojets represented viable technology for aircraft propulsion. But proving a concept in laboratory conditions differs dramatically from implementing it in combat aircraft subjected to the violent stresses of warfare. The jet engine demanded materials, precision, and reliability that would test German engineering to its absolute limits. Germany's aviation industry in the late 1930s represented the world's most advanced. Luftwaffe fighters dominated early war skies over Poland, France, and Britain. German pilots were better trained. German tactics were more refined. German aircraft were generally superior to their opponents on a one-to-one basis. The Messerschmitt Bf 109 and Focke-Wulf Fu 190 established German air superiority across multiple theatres of war, but by 1943, that superiority was eroding rapidly. American B-17 Flying Fortresses and B-24 Liberators bombed German industry in growing numbers. British Lancaster bombers burned German cities throughout the nights. Allied fighter escorts grew more numerous and capable. German pilots found themselves overwhelmed not by superior enemy equipment or tactics, but by sheer numerical inferiority that no amount of skill could overcome. The Me-262, offered a potential solution to Germany's deteriorating air situation. A jet fighter traveling 120 miles per hour faster than the finest Allied piston fighters could engage or disengage at will. It could climb above bomber formations, attack with devastating firepower, then escape before escort fighters could intervene. German pilots flying Me-262s could dictate the terms of engagement, choosing when to fight and when to withdraw, based purely on tactical advantage rather than desperation. Development of the jet fighter proceeded in fits and starts throughout the early war years. The first Me-262 prototype flew on April 18, 1941, powered initially by a single Junkers Jumo 210G piston engine of approximately 700 horsepower, as the jet engines were not yet ready. The aircraft's first flight under pure jet power occurred on July 18, 1942, more than a year later, using the Junkers Jumo 004 axial flow turbojet engines. Those engines represented Germany's greatest achievement and most crippling weakness in jet aviation. Dr. Anselm Franz at Junkers Motoren had created the world's first production turbojet engine using axial flow compressor technology. The Jumo 004 featured an 8-stage compressor section that compressed intake air progressively through successive turbine stages. 6 combustion chambers burned fuel mixed with the compressed air. A single-stage turbine extracted energy from the expanding exhaust gases, driving the compressor through a central shaft. The remaining exhaust blasted rearward through a variable geometry nozzle, producing thrust. The concept was elegant. The execution was extraordinarily complex. The Jumo 004 demanded materials that could withstand extreme temperatures and stresses while spinning at tremendous speeds. Turbine blades at the hot section experienced temperatures exceeding 1,800 degrees Fahrenheit while rotating under forces that threatened to tear them apart. Compressor blades needed strength to resist vibration and flexibility to handle varying air pressures. The combustion chambers required materials that wouldn't melt, buckle, or crack under sustained extreme heat. In an ideal world, with unlimited access to strategic materials, German engineers would have built these components from high-temperature alloys containing substantial percentages of nickel, cobalt, molybdenum, and chromium. These metals provided the heat resistance and structural strength that jet engines demanded. The initial Jumo 004A engines, built to power the Me-262 prototypes, used these scarce raw materials without restriction, and they worked beautifully. The 004A engines passed 100-hour tests in early 1943. Time between overhauls reached 50 hours. The engines produced reliable thrust and demonstrated that axial flow turbojets could power combat aircraft successfully. German engineers had solved the fundamental technological challenges. The engines worked, but Germany no longer had access to the materials required to build them in quantity. The Allied economic blockade, combined with the loss of conquered territories that had supplied strategic materials, left German industry critically short of nickel and chromium from the summer of 1941 onward. These elements were essential ingredients for high-temperature resistant steel alloys, yet Germany could no longer obtain them in quantities sufficient for mass production. Dr. Anselm Franz faced an impossible choice. Either abandon the jet program entirely, accepting that Germany would fight the rest of the war with increasingly obsolete piston engine fighters, or redesign the Jumo 004 to use substitute materials, accepting dramatically reduced engine lifespan as the price of production feasibility. He chose the latter. The Jumo 004B production engine represented a comprehensive redesign to minimize strategic materials. All hot metal parts, including the combustion chambers, were changed to mild steel, protected by an aluminum coating applied in the factory. The hollow turbine blades were produced from folded and welded chromadur alloy, developed by Krupp specifically for this application. Chromadur contained 12% chromium, 18% manganese, and 70% iron. Crucially, it contained only traces of nickel. The turbine blades were cooled by compressed air bled from the 4th compressor stage, allowing the inadequate alloy to survive temperatures it otherwise could not withstand. The engine's operational lifespan was shortened drastically, but production became possible. The 004B weighed 220 pounds less than the 004A. It used vastly less strategic materials, and it could be manufactured in quantity by semi-skilled workers in factories increasingly staffed by forced labour as the war consumed Germany's skilled workforce. The Reichsluftfahrtministerium accepted this compromise because no alternative existed. Germany would build jet engines from inferior materials and accept their short lifespans, or Germany would build no jet engines at all. The strategic situation by 1943 left no room for idealistic perfectionism. Germany needed jet fighters immediately, even if those jets had fatal flaws. Production engines began reaching Luftwaffe units in early 1944. Pilots who flew the Me-262 experienced a revelation. The aircraft was magnificent, faster than anything in Allied service. Heavily armed with 4 Rheinmetall Borsig Mk 108 30mm cannons, each capable of firing more than 650 rounds per minute. Delightful to fly, according to test pilots, with excellent handling characteristics once airborne and cruising speed that made it nearly invulnerable to interception. But the engines were another matter entirely. The Jumo 004B suffered from problems endemic to early jet engine design, magnified catastrophically by the use of substitute materials. Throttle response was sluggish. Advancing the throttle too quickly could inject excessive fuel into the combustion chambers before airflow increased to match. The resulting overheating softened turbine blades, causing catastrophic failure. Pilots had to nurse the throttles with delicate care, learning through brutal experience that abrupt power changes meant engine fires and forced landings. The turbine blades experienced thermal creep under operational conditions. The inadequate chromadur alloy gradually deformed under sustained high temperatures and centrifugal forces, slowly elongating until the blades contacted the engine casing or vibration, caused structural failure. The combustion chambers, made from mild steel with aluminum coating, slowly buckled out of shape as the engines ran. The extreme temperatures generated in the hottest section of the 004 exceeded what the inelegant substitute materials could survive for extended periods. Factory specifications stated that the Jumo 004B required overhaul after 25 hours of operation. In field conditions, with combat pilots who had not yet fully mastered the delicate art of jet engine operation, that figure dropped dramatically. Many engines failed after only 10 to 12 hours. Some units reported average engine life as low as 8 hours before flames erupted from exhaust pipes or turbines disintegrated, spraying white-hot metal fragments through engine nacelles. Pilots learned to expect engine changes as routine maintenance rather than exceptional events. An Me-262 that completed 10 combat missions without requiring new engines was considered remarkably reliable. Most jets spent more time in maintenance hangars with mechanics swapping failed engines than they spent flying combat operations. And every failed engine meant precious strategic materials were consumed, never to be recovered or reused. The Luftwaffe quartermaster records for January 10, 1945, tell the story with brutal clarity. German factories had delivered more than 500 Me-262s to operational units by that date. Yet only approximately 60 aircraft served with frontline squadrons, 52 fighter bombers, 4 night fighters, 5 employed for tactical reconnaissance. No, Me-262s were operational in the day fighter role, though day fighter interception represented the primary mission for which the aircraft had been designed. The missing 440 aircraft sat grounded, waiting for engines that factories could not produce quickly enough, waiting for spare parts that supply chains could no longer deliver, waiting for mechanics who possessed the expertise to repair complex jet systems, waiting for fuel that oil refineries could no longer provide in sufficient quantities. The Me-262 force on paper vastly exceeded the Me-262 force capable of flight. This was the reality of German jet aviation that Hans Fay understood when he pointed his unpainted Me-262 northwest toward Frankfurt instead of southeast toward Neuburg on March 31, 1945. The aircraft was magnificent, the engines were doomed, and Germany was defeated regardless of what technological marvels its engineers could still design. The Americans were about to learn these lessons firsthand. Hans Fay had waited for this moment, planning his defection with meticulous care tempered by fear for his family's safety. As a Messerschmitt test pilot and technical inspector, Fay possessed intimate knowledge of the Me-262's capabilities and limitations. He had flown the jet extensively during development testing. He understood what the aircraft could accomplish. More importantly, he understood what Germany could no longer achieve, regardless of technological advantages. His decision to defect carried enormous personal risk. The Nazi regime executed defectors and punished their families with savage enthusiasm. But when Fay learned that American forces controlled his parents' town, he felt safe enough to proceed with his plan. On the morning of March 31st, Fay joined 21 other pilots scheduled to ferry new Me-262s from the assembly factory at Schwäbisch Hall Hessenthal to a safer location at Neuburg and Donau as advancing Allied forces threatened to capture the aircraft. His aircraft lacked standard camouflage paint. Allied bombs had destroyed the paint shop building at the factory. Only low-visibility Balkenkreuz markings on wings and fuselage identified it as German. The unpainted aluminum skin gleamed in the spring sunlight, a fitting metaphor for Germany's stripped-down industrial situation. No paint, no excess materials, no time for anything beyond the absolute minimum required to get aircraft flying. Fay was the fourth pilot to take off that morning, but instead of following his comrades toward Neuburg, he turned northwest. The other pilots would notice his deviation, eventually. But by then, Fay would be beyond recall. He arrived at Frankfurt-Rhein main airfield at 1:45 in the afternoon, descended through clear skies, and surrendered himself and his aircraft to stunned American ground controllers who scrambled to secure the unexpected prize. Within hours, Colonel Harold E. Watson received notification that an intact operational Me-262 had fallen into American hands. Watson commanded the Air Technical Intelligence Division's field teams, nicknamed Watson's Whizzers by appreciative colleagues who marveled at their ability to locate, secure, and recover advanced German technology from the chaos of collapsing Nazi Germany. Watson understood immediately what Fay's defection represented. The Me-262 was the most advanced fighter aircraft in operational service anywhere in the world. American intelligence had been tracking its development and combat employment for months. Allied bomber crews reported being attacked by impossibly fast German jets that appeared from nowhere, delivered devastating attacks, then vanished before escort fighters could respond. Allied fighter pilots described frustrating engagements where German jets simply accelerated away from pursuit, rendering even the fastest piston fighters helpless. Now the Americans possessed a complete, undamaged example. Better yet, they had captured it in flyable condition, delivered by an experienced test pilot who could provide detailed technical information about systems, procedures, and operational limitations. And the aircraft had been built recently, incorporating the latest production modifications rather than being an early prototype with outdated systems. American technical intelligence personnel photographed work number 111711 from every angle. They measured dimensions with precision instruments. They documented systems without touching anything, preserving the aircraft in exactly the condition Fay had delivered it. Only after exhaustive photographic documentation did they begin disassembling components for detailed examination. The aircraft was transported to Cherbourg, France, then loaded aboard the British aircraft carrier HMS Reaper for the transatlantic voyage to the United States. It arrived at Wright Field, Dayton, Ohio, designated FE 0107 by American intelligence, the FE prefix indicating foreign equipment. Later, the designation changed to T-2-711 under the Air Technical Service Command's Evaluation Program numbering system. But Watson's Whizzers were just beginning their collection efforts. As Nazi Germany collapsed in April and May of 1945, American and British teams raced across occupied territory, seizing advanced technology before it could be destroyed or captured by Soviet forces advancing from the east. Operation Lusty, the codename for Luftwaffe secret technology acquisition, represented one of the most successful technical intelligence operations in military history. Near Augsburg, At Lechfeld Airfield, Watson's teams discovered approximately 25 relatively intact Me-262s, including at least one coveted two-seat trainer variant. The airfield had been captured without opposition and renamed Advanced Landing Ground R-71 by occupying American forces. German ground crews and mechanics remained at the base, some willing to cooperate with the victors, others sullenly resigned to American occupation. The task facing Watson's whizzers seemed insurmountable. 15 Me-262s were designated for restoration to flyable condition and ferry flights back to collection points for eventual transport to the United States. But the jets had been deliberately sabotaged by retreating Germans, damaged in Allied air raids, or simply stripped for parts by mechanics desperate to keep other aircraft flying. Engines were missing, control surfaces had been removed, fuel systems were drained and damaged. The aircraft looked less like operational fighters and more like a scrapyard of exotic components scattered across the airfield. Master Sergeant Eugene Freiberger and his team from the 54th Air Disarmament Squadron tackled the problem with American pragmatism and German expertise. They employed former Luftwaffe mechanics to help with repairs, men who knew the Me-262's systems intimately and could diagnose problems that would baffle American technicians unfamiliar with German jet technology. They recruited German pilots to provide instruction and conduct test flights, including Karl Bauer, Messerschmitt's chief test pilot, who had been captured when American forces seized Messerschmitt's factory at Augsburg on April 29. Bauer was highly experienced, having flown most of Messerschmitt's designs, including the Bf-109, Me-209, Me-309, Me-210, Me-410, Me-261, Me-321, Me-323, and even the Me-163 rocket-powered interceptor. He had piloted the Me-264, Messerschmitt's contender for the America Bomber project. His expertise proved invaluable for getting damaged Me-262s airborne again. Another key German instructor was Ludwig Willi Hoffmann, a skilled test pilot who worked alongside American pilots, teaching them the peculiarities of jet flight and specifically the proper control of the Me-262's temperamental engines. For experienced American pilots accustomed to piston fighters, the most difficult aspect involved managing throttle settings to avoid flameouts, compressor stalls, and turbine failures that plagued the Jumo 004 engines. The Americans were fortunate to have access to a two-seat Me-262 for training. So few two-seat trainers had been produced that most Luftwaffe pilots made their first jet flight in single-seaters without an instructor aboard. The aircraft that became known as Vera, coded White, 35, had been built at a factory in Leipheim, with the two-seat conversion possibly performed by Blom and Voss. Prior to capture, it had served with Ergänzungs Jagdgeschwader II, a Me-262 training unit. Captured by American forces in May 1945, White 35 was the first jet brought into the hangar for restoration at Lechfeld. Sergeant Freiberger named it Vera, after his sister-in-law, as part of a tradition where captured aircraft received women's names painted on their noses. Other Me-262s in the recovery program were christened Joanna, Pauline, Julie, Doris, Connie, My Sharp Article, Marge, Beverly Ann, Wilma Jeanne, and Dennis, the last named after Freiberger's son. Test pilot Ludwig Hoffmann flew Vera on May 14th or 15th, accompanied by Captain Ward, an American operations officer who became the first American to fly the Me-262. The flight demonstrated that despite damage and months of neglect, the jets could be restored to operational condition through systematic work and German technical expertise. On the morning of June 10th, 1945, all serviceable Me-262s at Lechfeld began their journey to the United States. White 35 launched first at 9:25. The other aircraft followed with departures between 9:30 and 11:15. Each of these 9 jets had women's names painted on their sides, contributions from members of the 54th Air Disarmament Squadron who had worked to restore them. Vera was joined by Joanna, Pauline, Julie, Doris, Connie, My Sharp Article, Marge, and Wilma Jeanne. all completing the 515-mile journey to Melun-Villa-Roche airfield in France, marking each pilot's first cross-country jet flight. 2 more, May 262s, joined them at Melun-Villa-Roche, having been captured by British forces in Schleswig. The aircraft were followed by truckloads of spare parts, tools, documentation, maintenance equipment, and mechanics, both German and American. Everything needed to keep the jets flying was carefully preserved and transported. The captured Me-262s were eventually loaded aboard HMS Reaper for transport across the Atlantic. 40 German and 1 American aircraft made the crossing, including 10 Messerschmitt Me-262s, 5 Focke-Wulf Furve 190F ground attack fighters, 4 Focke-Wulf FW-190D long-nose fighters, 1 Focke-Wulf TAR 152H high-altitude interceptor, 4 Arado R-234B jet reconnaissance bombers, 3 Heinkel He-2, 19 night fighters, and various other German types that represented the final evolution of Luftwaffe technology. Upon arrival in the United States, the Me-262s were divided between the Army Air Forces and the Navy. The Army received the majority for testing at Wright Field in Dayton, Ohio. The Navy took 3 jets to the Naval Air Station at Patuxent River, Maryland, for their own evaluation program. Vera, designated Navy Bureau number 121448, went to the Navy initially, before later transfer to other facilities. Wright Field, Dayton, Ohio, served as the United States Army Air Force's premier testing and evaluation center, equivalent to Germany's Rechlin facility. When the captured Me-262s arrived in summer 1945, American engineers and test pilots approached them with a mixture of excitement and professional caution. These were the jets that had terrorized Allied bomber formations, the fighters that could outrun anything in American service, the technological marvels that represented Germany's last hope for air superiority. The Americans possessed their own jet fighter by this time. The Lockheed P-80 Shooting Star had first flown in January 1944, powered initially by a British de Havilland Goblin engine, later replaced by the American-made General Electric J-33 turbojet. The P-80 had been designed in just 143 days by Kelly Johnson's Skunk Works team at Lockheed, a remarkable achievement in rapid development. But the P-80 had missed combat in World War II entirely. 4 YP-80A aircraft reached Europe in early 1945 for operational testing and possible combat deployment. 2 went to England, 2 to Italy. The jets were intended for familiarization flights, reconnaissance, and potentially interception of German jets if the war continued long enough. But on January 28, 1945, Major Frederick Borsodi was killed in a crash at RAF Burtonwood, Lancashire, England, when an engine fire caused structural failure during a demonstration flight. The YP-80A fleet was temporarily grounded following this accident. The P-80 saw no actual combat during the war. Only 83 P-80As had been delivered by the end of July 1945. While the American jet showed promise, it remained largely unproven. The captured Me-262s offered an opportunity for direct comparison between German and American approaches to jet fighter design. 2 Me-262s became the primary subjects of Wright Field's test program, T-2-711. Hans Fay's original defection aircraft served as the main platform for handling and performance tests. T-2-4012, a reconnaissance variant with an unarmed nose section, provided comparative data and backup testing capability. The American evaluation team, led by T2 Intelligence at Wright Field, established comprehensive test protocols designed to thoroughly understand the Me-262's capabilities, limitations, and potential vulnerabilities. Test pilots would fly the aircraft through its full performance envelope. Engineers would analyze every system. Maintenance personnel would document reliability issues and compare German manufacturing techniques with American practices. First, Lieutenant Walter J. Macaulay, Jr. became one of the primary test pilots for the program. Born March 10, 1917, at Fort Worth, Texas, Macaulay had attended Texas A&M College, graduating with a Bachelor of Science degree, in 1941. He received his pilot wings on July 29, 1943, and accumulated 61 combat hours before being assigned to Wright Field as a test pilot. By the time he flew the Me-262, he had 671 total flight hours, including 2 hours and 45 minutes in the German jet. The testing began with careful evaluation flights designed to understand the aircraft's handling characteristics. American pilots found the Me-262 delightful to fly once airborne and at altitude. The swept-wing design provided excellent high-speed performance. Control responses felt predictable and balanced. The aircraft could reach speeds exceeding 540 miles per hour, significantly faster than the P-80's maximum speed of approximately 600 miles per hour in later variants. But from the first flight, the engines proved problematic. The Jumo 004B turbojets suffered from all the issues that had plagued German operations, magnified by the challenges of operating captured equipment without complete technical documentation or adequate spare parts inventory. The engines were temperamental, requiring careful throttle management to avoid compressor stalls and turbine failures. They consumed fuel at alarming rates, and they failed with disturbing frequency. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. T-22711 required 5 engine changes during its test program. T-24012 needed 4 engine replacements. These figures are staggering when considered in context. T-22711 flew 12 test flights totaling only 10 hours and 40 minutes before its final catastrophic failure. T-24012 flew 8 times for 4 hours and 40 minutes total. During 20 test flights across both aircraft, 9 engines failed and required replacement. American engineers conducting post-flight inspections discovered the problems that German mechanics had learned to expect. Turbine blades showed visible elongation from thermal creep, gradually deforming under sustained high temperatures and centrifugal stress. Combustion chambers had buckled out of shape, distorting the precise geometry required for efficient fuel burning. Compressor blades exhibited damage from foreign object ingestion, as the wire mesh screens covering the intakes could not prevent all debris from entering the engines during ground operations. The metallurgical analysis revealed the fundamental problem. The chromodur alloy used in turbine blades simply could not withstand the extreme operating environment for extended periods. The mild steel combustion chambers with aluminum coating failed progressively as the protective coating burned away. The substitute materials that allowed mass production also guaranteed early failure. American metallurgists examining failed components recognized materials they would never have approved for such demanding applications. The turbine blades lacked the nickel content required for high-temperature strength. The combustion chambers used steel grades appropriate for automotive applications, not aircraft jet engines operating at temperatures exceeding 1,800 degrees Fahrenheit. Every component reflected Germany's desperate material situation. German documentation, captured with the aircraft, specified that the Jumo 004B required overhaul after 25 hours of operation. At that point, the engine would be removed, disassembled, and critically examined. Turbine blades would be replaced, combustion chambers would be changed, compressor blades would be inspected and replaced if damaged. The entire engine would be rebuilt using fresh components before being reinstalled for another brief operational period. If the engine passed its 25-hour inspection, it could be cleared for an additional 10 hours of flight time. 35 hours represented the absolute maximum lifespan for the turbine wheel and other critical components that could not be replaced during field overhaul. After 35 hours, the engine was supposed to be scrapped, its materials reclaimed for manufacturing new engines. But American testing revealed that even these pessimistic German specifications overstated actual reliability. In field conditions, with combat pilots who had not yet fully mastered jet engine management, average engine life dropped to approximately 10 to 17 hours before failure. Some engines failed after only 8 hours. The Russian Aviation Technical Services, which examined captured Jumo 004B engines and built copies designated RD-10, confirmed these dismal figures. German assembled engines from captured parts averaged approximately 17 hours before failure. Soviet copies, built with even lower quality materials, performed worse. The contrast with American and British jet engine development was stark. The British Rolls-Royce Derwent engine, an evolution of Frank Whittle's pioneering designs, achieved time between overhauls measured in hundreds of hours, not tens. The American General Electric J-33, which powered the P-80 Shooting Star, initially achieved only 15 hours between overhauls in 1948, but this improved rapidly to 225 hours by the early 1950s, with theoretical lifespan reaching 1,200 hours by 1956. The fundamental difference lay in materials. British and American engineers had access to nickel superalloys like Nimonic and Inconel, developed specifically for high-temperature applications in jet engines. These alloys contained substantial percentages of nickel, chromium, and other elements that provided the heat resistance and structural strength that jet turbines demanded. The alloys were expensive and required sophisticated manufacturing processes, but they worked reliably for hundreds of operational hours. Germany lacked access to these materials and lacked the years of development time required to create adequate substitutes. The Allied economic blockade had cut off nickel supplies from 1941 onward. Chromium remained available only in limited quantities. Cobalt and molybdenum were critically scarce. German metallurgists understood perfectly what materials their engines needed. They simply could not obtain those materials in quantities sufficient for mass production, so they compromised. They redesigned the engines to use whatever materials were available. They accepted drastically reduced lifespan as the unavoidable price of producing engines at all. And they sent pilots into combat knowing their aircraft carried engines that might fail at any moment. The testing at Wright Field confirmed what German engineers already knew. The Me-262's greatest weakness was not its aerodynamics, which were excellent, not its armament, which was devastating, not its speed, which exceeded all Allied fighters. The aircraft's fatal flaw was the engines, which represented a triumph of German engineering ingenuity applied to an impossible material situation. On August 20, 1946, the test program reached its inevitable conclusion. First Lieutenant Macaulay took off from Patterson Field at 12:05 Eastern Standard Time, flying T-2-711, accompanied by Major Richard L. Johnson in a Lockheed P-80 chaseplane. The unpainted Me-262 gleamed in the summer sunlight as it climbed away from the field. At 12,000 feet, Macaulay noticed the right engine losing power. Then grey smoke began trailing from the left engine. Glancing at his instruments, he saw the left engine tailpipe temperature gauge reading 0, indicating complete instrument failure or catastrophic engine malfunction. He immediately shut down the left engine and began a glide without power from either engine. Macaulay notified Patterson Field of his emergency situation. Major Johnson in the P-80 returned to formate on the crippled Me-262 and observed a long trail of smoke extending behind the jet. Macaulay attempted to restart the right engine. A start was obtained, but the engine continued to torch, flames extending 2 to 3 feet behind the tail, running at only 2,500 RPM when it should have been producing 8,700 RPM for full power. The crippled jet descended through the summer sky over Ohio, trailing smoke and flame. At approximately 3,000 feet, with both engines failed and the aircraft rapidly losing altitude, Macaulay made the decision to abandon the aircraft. He jettisoned the canopy, released his restraints, and ejected from the doomed fighter. His parachute deployed successfully. He floated down to safety, suffering only minor injuries. Below him, T-2-711, the first intact, Me-262 to fall into Allied hands. The aircraft that Hans Fay had delivered 16 months earlier impacted 2 miles east of Lumberton, Ohio, near Route 68. The aircraft was completely destroyed in the crash. The testing program was immediately suspended. T-24012 had already made 2 single-engine landings during its test flights, demonstrating that engine failures were not isolated incidents, but systemic problems inherent to the Jumo 004B design. The limited value gained from further testing of German jets with such unreliable engines was not worth the risk of losing more pilots. Section 5. Aftermath and Legacy. In February 1947, T-2 Intelligence at Wright Field produced a comprehensive report on the Me-262 exploitation program, entitled Evaluation of the Me-262, project number NAD-29. Engineer Roy W. Adams provided detailed analysis of the aircraft's characteristics and performance based on the 20 test flights conducted across both evaluation aircraft. The report's conclusions were measured and professional. The Me-262 represented a significant technological achievement in airframe design. Its swept-wing configuration provided excellent high-speed performance. The aircraft handled well at altitude and demonstrated superior speed compared to contemporary Allied fighters. The armament of 4 30mm cannons delivered devastating firepower. The design incorporated thoughtful engineering solutions throughout. But the engines. The report returned repeatedly to the engines. The Jumo 004B represented an engineering compromise that sacrificed long-term reliability for short-term production feasibility. The substitute materials, used in critical components, resulted in unacceptably short operational lifespans. The engines required intensive maintenance that was difficult to provide under field conditions. And most critically, the engines failed with alarming frequency, posing unacceptable risks to pilots and operational effectiveness. American engineers who examined the captured Jumo 004 engines recognized immediately why they failed so quickly. The turbine blades, made from chromodur alloy with minimal nickel content, could not withstand the extreme thermal and mechanical stresses of sustained operation. The combustion chambers, fabricated from mild steel with baked aluminum coating, deteriorated rapidly under temperatures they were never designed to handle. Every component reflected Germany's desperate material shortage. Frank Whittle, the British jet pioneer who had invented the turbojet engine in parallel with Germany's Hans von Ohain, reviewed intelligence reports on German jet engine development after the war. His assessment was blunt. It was in the quality of high-temperature materials that the difference between German and British engines was most marked, he wrote. The Germans had matched or exceeded British and American engineering sophistication in many areas of jet engine design, but they could not overcome the fundamental handicap of lacking adequate high-temperature alloys. The Me-262's influence on post-war aviation development proved substantial despite its operational failures. The swept-wing design influenced numerous American aircraft, including the North American F-86 Sabre, which incorporated wing slats based directly on Me-262 technology. Soviet designers studied captured examples intensively, with the knowledge gained informing the MiG-15 and other early Soviet jets. The Boeing B-47 Stratojet bomber utilized swept-wing principles pioneered by German researchers. But the engine lessons proved equally valuable, though in a negative sense. American and British engineers learned what not to do when designing jet engines. They learned that substitute materials produced false economy, creating engines that consumed more resources through frequent replacement than properly designed engines, using expensive but durable alloys. They learned that cutting corners on critical components guaranteed operational failures that endangered pilots and missions. The captured Me-262s taught American engineers to appreciate the importance of adequate materials more than any theoretical study could have accomplished. Seeing German engineering excellence crippled by material scarcity provided a visceral demonstration of why the United States needed to maintain access to strategic materials and develop reliable supply chains for critical alloys. American defense planners after World War II ensured that strategic material stockpiles included adequate reserves of nickel, chromium, cobalt, and other elements essential for jet engine manufacturing. The human cost of Germany's material shortages becomes apparent when examining Luftwaffe records. Approximately 1,400 Me-262s were manufactured by war's end, but never more than 50 to 60 operated with frontline units at any given time. Most sat grounded, waiting for engines that would never arrive, waiting for parts that could no longer be manufactured, waiting for fuel that refineries could no longer produce. Of the aircraft that did fly combat missions, engine failures claimed many. Luftwaffe pilots reported that roughly 1 in 5 Me-262s would suffer engine failure during takeoff or landing, the most dangerous phases of flight when the aircraft flew too slowly to glide safely to an emergency landing site. Pilots learned to fear engine failures more than enemy fire. At least enemy fighters could be evaded using the Me-262's superior speed. Engine failures offered no escape, no countermeasure, no hope except abandoning the aircraft if altitude permitted. The captured aircraft that American and British forces seized in spring 1945 represented only a fraction of total Me-262 production. But they provided insights that shaped Western understanding of both German technological achievements and German industrial collapse. The jets demonstrated that Germany retained world-class engineering talent capable of designing revolutionary aircraft. They also demonstrated that engineering excellence means nothing when industrial capacity fails. Hans Fay, the test pilot who delivered the first intact Me-262 to American hands, survived the war and returned to civilian life. He died March 30, 1981, in Altea, Spain, having lived to see jet aviation evolve from the temperamental, short-lived engines he had flown into reliable power plants that enabled global air travel and military superiority. The Me-262s that survived the war now rest in museums around the world. 9 original aircraft exist as of this writing, carefully preserved examples of humanity's first operational jet fighter. The Smithsonian's National Air and Space Museum displays work number 500491, coded Yellow 7, which served with Jagdgeschwader 7. According to kill markings on the fuselage, pilot Oberfeldwebel Heinz Arnold scored 42 victories over Soviet piston engine fighters and 7 over American bombers and fighters while flying this aircraft. The National Museum of the United States Air Force at Wright-Patterson Air Force Base displays work number 501232, coded Yellow 5, which served with the 3rd Squadron of Kampfgeschwader 6. The Deutsches Museum in Munich preserves work number 50071, coded White 3, which Hans Guido Mutke flew when he made an emergency landing in Switzerland on April 25, 1945, after, allegedly, breaking the sound barrier during a desperate dive to protect another Me-262 from attack. The claim remains unverified, but demonstrates the aircraft's extraordinary performance capabilities. These preserved examples allow modern observers to see firsthand what German engineers accomplished despite crippling material shortages. The aircraft are beautiful, their swept wings and streamlined fuselages suggesting speed even while standing motionless. The engineering is sophisticated, with thoughtful solutions visible throughout the designs. But the Jumo 004 engines, carefully preserved alongside the airframes, tell a different story. These are engines that never should have flown. Engines built from inadequate materials. Engines that represented Germany's desperation made manifest in aluminum and steel. The story of captured Me-262s in American hands illuminates a fundamental truth about modern warfare that remains relevant today. Nations win wars through industrial capacity applied systematically over time, not through isolated technological breakthroughs achieved through brilliant engineering. The Me-262 was faster than any Allied fighter. It was more heavily armed. It incorporated more advanced aerodynamics. And it made absolutely no difference to the war's outcome because Germany could not produce reliable engines in quantities sufficient to deploy the jets effectively. American industry by 1945 operated on a scale that dwarfed German capacity. The United States produced 96,000 aircraft in 1944 alone, including fighters, bombers, transports, and trainers. Germany managed approximately 25,000 aircraft of all types that same year. American factories built more than 125,000 Pratt & Whitney R2800 radial engines, just one engine type, exceeding Germany's entire combat aircraft engine production for the war. The aluminum, steel, and strategic materials that flowed through American factories would have seemed like impossible abundance to German engineers forced to build jet engines from mild steel and substitute alloys. The machine tools that manufactured components to precise tolerances, the quality control systems that ensured consistent manufacturing standards, the logistics networks that delivered parts when and where needed, the skilled workforce that could be trained, housed, and fed without threat of strategic bombing. Every aspect of American industrial capacity exceeded German capabilities by factors that made technological superiority increasingly irrelevant. The Me-262 represented Germany's final attempt to achieve through engineering brilliance what they could no longer accomplish through industrial might. The attempt failed because engineering cannot conjure strategic materials from thin air. Design cannot substitute for manufacturing capacity, and revolutionary technology introduced by a defeated nation arrives too late to matter, regardless of how advanced it might be. When Wright field engineers examined the failed Jumo 004 engines after the test program ended, they found turbine blades elongated beyond safe limits, combustion chambers buckled and distorted, and compressor stages damaged by operational stresses. They saw expensive engines that had consumed tremendous engineering talent and precious materials to produce, then failed after mere hours of operation. They saw German desperation quantified in deformed metal and inadequate alloys. The engineers wrote their reports professionally, documenting what they had learned without mockery or schadenfreude. But the implicit message was clear. Germany had attempted the impossible. They had tried to build jet engines without jet engine materials. They had tried to wage industrial warfare without industrial capacity. They had tried to win through technological sophistication, while their enemies won through systematic application of overwhelming material advantage. The Americans had watched this drama unfold from a position of absolute security. Their factories operated untouched by enemy bombs, their supply lines stretched across oceans that enemy forces could not threaten. Their access to strategic materials remained secure through control of global trade routes and careful stockpiling. When American engineers needed nickel for jet engine development, they obtained it. When they needed chromium, cobalt, or any other strategic material, their procurement systems delivered it. The captured Me-262s taught American engineers to never take this advantage for granted. Material security underpins technological capability. Strategic stockpiles enable innovation, and industrial capacity, maintained through peacetime and mobilized during war, determines which nations survive conflicts and which nations collapse under the weight of industrial attrition. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The legacy of the Me-262 extends far beyond the aircraft itself. It represents a cautionary tale about technological hubris confronting material reality. It demonstrates how engineering excellence, without adequate resources, produces weapons that impress observers but fail operators. And it provides a sobering reminder that wars are won by nations that can sustain production, maintain quality, and replace losses faster than enemies can inflict them. The Germans built a jet fighter a generation ahead of its time. Then they crippled it with engines that barely outlasted a weekend training flight. The Americans tested those jets, watched the engines fail repeatedly, examined the inadequate materials, and learned lessons that would shape their own jet programs for decades. Technology matters, but resources matter more. And the nation that forgets this lesson invites disaster regardless of how sophisticated their weapons might appear. The Me-262's engines lasted 25 hours, sometimes less, often much less. This single statistic explains Germany's defeat more eloquently than any strategic analysis. They had the engineering talent to design the future. They lacked the industrial capacity to build it. And, in modern warfare, capacity defeats brilliance every single time.